Hello and welcome to TRX Bench. Today here on the bench we have an Albrecht AE497W. So that is a 25 watt version of CB radio, but this version is of course called 10 meter radio, and that is what we can read here above our display. So that is a 10 meter AM FM SSB base station radio, and this radio really is suffering from some different issues. So receive and transmit is completely disaligned, and some pots are dirty. So I believe we need to have a closer look to what's really going on, and then we will go step by step through and see that we get this radio back working. Okay, and as I already said here, our pots are dirty, so we definitely have to give them a clean. And additional to that, it really looks like that the radio is totally disaligned. So let's have a look to our tester. Okay, and here we have the situation. So okay, we are with a relatively low level, and we have the radio on SSB upper sideband. So 27206 should be the right frequency to get our beating frequency of 1 kilohertz. So that is representing our audio frequency, right? And what we see is that we are 730 hertz above our dialed in frequency. So that means that it is obviously really 730 hertz off. But we want to check it as well on transmit to verify that what we are looking for is right. Okay, and for best accuracy we have connected here our counter, and I now feed in 1 kilohertz, and our dialed in frequency is 27205, and as we are on SSB, our upper sideband frequency, which we will read on our counter, will be 27.206 megahertz. So let me transmit into the radio, and so what we see here is that we are really 711 hertz off, and with 1 kilohertz of course. So I'm feeding in 1 kilohertz, and you see when I'm talking that the frequency is changing. So that is what you see, and without talking 710, 711. So that is what our oscillator is off. And of course we are on SSB. And remember, all above or below 30 hertz off means it will be heard on the band. So therefore it is really crucial to get the frequency as close as possible. And therefore it is definitely clear that the radio is disaligned, and that is what we need to check. Okay, let me try to clarify a little bit more what the problem really is. So our radio is set to 27205 megahertz, right? And it is set to upper sideband. And now I have set here my generator into the SSB mode. So that is seen here up there. So we are on RX SSB test mode, right? So I've set here our R frequency of 27205, so that is what we see on the radio, and I have set the mode to upper sideband. Now the radio is set on the same frequency, and we should, when it is set to SSB function, we should be able to hear the tone, okay? But what we see here is that we do not have an AF level, and we do not see that our counter is showing 1 kilohertz, right? Because we should see 1 kilohertz on the AF side, right? We are really putting 1 kilohertz into our generator, which is of course acting as a transmitter, as you like, into our radio. And we have set the same signal level, RF signal level, as we had it before, minus 115 dBm. What we have seen is that our frequency is 710 or even more hertz off. And what does it mean? Exactly what you hear here. The problem is the only what you can hear is noise, and you see it. This is our audio. We have noise, nothing else. And now if I go and change here my frequency to the delta, what we have recognized before, see what happens. So let me here slowly increase our carrier or our SSB frequency, okay? And what you might already hear, that there is a tone, a very low tone in the background. So let me go up more. And what we hear is, and you can read it here, 400 hertz. So that is the audio tone. So you see, with upcoming, let me call it carrier frequency, we know that is not carrier, but with upcoming carrier frequency, we see, now we are already at 500 hertz, and we see that our audio level is getting up, and you see here that, our audio is getting in somewhat. Let me increase it more, and you see our frequency is coming up. And remember, so we have here 1 kilohertz, so that is what we injecting to our carrier, right? And we know the carrier is of course suppressed, so that is the reason why it is on 27206, right? Anyways, let's go further here, and what we see is that we are getting closer to our 1 kilohertz. And now, so now it is 1 kilohertz audio frequency, and we see we are 850 hertz off according to this counter, right? And now we are in frequency, and that means if a SSB radio is that much off frequency, you do not hear nothing on your radio. And that is not only on receive, the same problem is when you try to transmit. So you are always off frequency, and that means that maybe you have organized a scat with a radio friend, and you have said, let's meet on 27205, and you try to call your friend on the radio on 27205, your friend who has dialed in, of course, 27205 will never hear you because your radio is too much off. And that is a proof that, you know, really a frequency which is that much off will really bring you in the situation that you never will be heard and you might not hear anybody. So that is really the problem. And let's try if we can simulate it here. I mean, this is 850 hertz, and I said that already 30 hertz is will be heard. So let me do it here a little louder, and let's go down here to 820, which is then can you hear that? Maybe let me increase the level a little bit more for a better signal to noise ratio. So you hear we are improving our signal to noise ratio by increasing our RF level. Once again, let me go back here to 850. Okay, so 860, and we are back here to 1009 hertz, which is fine. Now let me go back here. And do you hear that it is really to be heard on the band? And that is what, let me switch it off here, annoying tone. So that is what I always say. If we talk about SSB, it is so important to be spot on frequency, because if you are over 30 plus or minus hertz, you definitely hear it on the band, and therefore you always should try to have your radio aligned, especially for SSB radio. If it is FM, so you will not really recognize it. So you can 250, 300, 400 hertz off, and you might not really hear it on the radio. But on SSB, it is totally different, and therefore that is the reason why it is so important. Okay, and the next figure we want to look into is on transmit. So now our tester here is acting as receiver, and our radio will act as transmitter, right? So I will inject into our microphone 1 kilohertz, and that is important, so you know that SSB signal is always with suppressed carrier, so we need our audio tone hooked on our carrier, if you like. And now it is important. I mean, we will see our frequency error as well, as we have seen it on our frequency counter before. But then we want to see what we send out here with our radio. What will be the audio quality, because we can evaluate our distortion, and that is, you know, our transmission distortion of our signal. And so we have, of course, here in our CMS we have, of course, a demodulator, SSB detector, or however you want to call it, and we are interested in the distortion. So is that what is getting out of our radio, is that clean or not? So therefore, let me now go into transmission. That is a little bit difficult here to hold it. Okay, so what we see here, our output power is 11 watt something, and we see here our frequency arrow once again, and with our 1 kilohertz we see a distortion over the air. So that is what we have of, yeah, I should not talk because that is influencing here our value. So we are under 5% over air, and that is just fine. So we obviously do not have a problem on that portion of our radio, so that is good. Therefore, of course, our next step is let's crack it open and let's see what version we have in, because there are different versions, different main boards over the years. So let's have a look what we have inside. Alright, so here is our inside of our radio. So it is a relatively massive net transformer, so that is just fine. So we have here our DC power supply with the big rectifier and the power transistor here, and that is a newer version of this radio. And well, how do we know that? Very simple, we only need to see the final transistors which are in, and this both are the finals, and you see we have ERF 2030, and the ERF 2030 is a MOSFET, and only the later versions do have the MOSFET final. Earlier versions were equipped with a normal bipolar transistor. So we know it is, you know, a more modern one, and therefore now we can search for the right schematic, and of course for the right alignment procedure, and then let's go into it. Okay, and I've just started here with our PLL alignment, and well, the first what we have to do is to adjust our T14, so that is the reference voltage for our deviation. So that is an important value, so I've done that, and then directly after that we go into the LO frequencies, which are really important to get finally our radio frequency aligned. And here you can see it on the schematic. So here's our T14, here is the output of our audio amplifier from the microphone, and you see that here over RV3, which is a deviation adjustment, goes right up here over our T14 to another cap diode, and therefore that I have done. I've set it to 1.2 volt. That was already misaligned, and of course we will go ahead and adjust now our T17 for our first frequency. Okay, and here we have our VCO, and of course we have to align here our coils at the VCO, and we start with T17, so that will be the first what we have to adjust, and yeah, it needs to be at 37.660 megahertz, and yeah, let's see what it will be on our counter. Okay, so let me go down here to our test point, which is here. And okay, so we should see 37.660 megahertz, and you see here we have already an error of 863 hertz, which is more or less similar with you know, our error, what we have seen in our receive and in our transmit frequency. So that is the first what we try to align. So let's see, when I go down here, and you see I'm already at our T17, and you see that I'm able to align. I hope that we are able to really go down to 660. Let's see. Oh, it is really working quite nice. It is not too touchy, which is always nice if you have to align something. And okay, yeah, now you know that is always a little bit difficult to get here the last hertz aligned, but you know, it is not too hard to have 2 or 3 hertz off, so that is not the point. Okay, so you see how it works, and now I have to go to all the different transformers which we have to align here. So I do not show it. You know, that is a procedure we have to follow. Let me do it, and I will tell you afterwards what we have found here. Okay, so that is now the last transformer I have aligned. And the interesting point is we have 5 of these little transformers here on the radio, and all was around 800 something hertz off, and it looks a little bit like that the person who had done it before had a misaligned frequency counter. I mean, you know, it is so easy to have a counter which is not really aligned, that you can misalign your radio as well. I mean, my counter here is connected to an external standard, and you can see this light here, lighting, indicating that we are sitting here on an external standard which is rock solid, and therefore it is really important to have a counter which has really a high accurate reference, and additional to that you need of course a high resolution, otherwise you are not able to align radios like this. You always need minimum a counter which is able to show 1 hertz, and that is here our last digit, which is representing the 1 hertz area. Right, so now all are really nicely aligned, and we can go ahead. Just to see it here on the board, so we are talking about these 5 transformers here, which are now accurate aligned to what our aligning procedure is telling us, and that is really crucial to have at least the right frequency on air, right? Okay, so after we have done here our master oscillator alignments, we go over now to the carrier oscillator. The carrier oscillator is very important because we are setting for LSB and USB for our SSB mode. So this both frequencies are absolutely crucial, and you see that they write here that there is a tolerance allowed of 20 Hertz, and that is what I've showed you, that you already hear 30 Hertz, right? And therefore it is only logical that they state here that 20 Hertz is allowed, but it should not be more, right? Alright, and what we see here, that is our carrier oscillator, which is needed here. You see LSB and USB, so this both frequencies are really important to be able to feed our balance modulator, which is needed simply for SSB, and therefore this frequencies needs to be absolutely stable and accurate, so we really need to put an eye on that. Okay, and radio is set to LSB, and now I go down here to our test point on the PCB, and yeah, now I'm down, and yeah, believe it or not, I have a real good contact down on the board, and you see our counter. So what's going on here? So I do not have reading. Let's check it with the scope, right? I'm still down at the test point, and I take over here our probe from the counter to our scope, and you see here we have a reading. That is interesting, isn't it? And if we go down and if we go up here to our frequency reading, so that is 10.6, can't read it, it's too small for my eyes. 10.69, I don't know, something. Anyways, here we have our oscillator frequency, which we were not able to read with our Racal, and if we check here the output voltage, you see that it is only 19, or let me say 20 millivolt RMS. So that is really very little, and our counter does not have the sensitivity to read such a low level, so you do not get a reading at all. Yeah, and now you see how much helpful it is to have finally a more modern counter. So my Agilent 5313 is much more sensitive than my Racal. So the Racal is a very good counter, and it is good for 99% of all tasks, but sometimes the sensitivity is not good enough, and when you have to work on oscillator circuits, then it is what you experience from time to time. And here you see we have 10.692.4. I mean, it is a little bit jumping back and forth, so we are very, very close. But to be honest, I have already pre-aligned it a little bit, so it was much more off. What you see is that, yeah, without the right equipment, it is always very difficult to do jobs right, especially jobs like this here. So, well, therefore, and even this counter is very close to its sensitivity. Yeah, edge, if you like. So therefore, and we cannot really align it with our scope, because we do not have the resolution at our scope. And secondly, you know, the master oscillator is not that accurate than we have it here with our counters, because here you see as well that we have an external reference. Don't know if you can see it. No. Okay, so you see it is indicating for external reference, and that is what I already told you. I've connected here my gear to a distributor, which is distributing here my clock frequency within my lab to have absolutely synchronized clock frequency, which is, on the other hand, rock solid. So that is what you need. Okay, and now we go and do our our final alignment here on our LSB carrier oscillator. Alright, and here is our LSB carrier oscillator at 10692.5 megahertz, and that is exactly what we need. And yeah, you see how critical that is, and therefore I can't tell it often enough that this is absolutely crucial to get the radio right. Okay, so radio is set to 26965, and we just want to see if what we have done makes any sense. So just remember 965, and we go over to the tester. Okay, and here we are, and now you see I do not need to offset my frequency what we had before, and one reference for that is that we are only 6 Hertz, 7 Hertz off, which you know is normal with radios like this. But you remember that we had with our intake check, we had here 800, 700 Hertz off, and we were not able to receive the frequency from our generator on the radio with the dialed in frequency on our radio. So now it is all as it should be. Okay, and let's test it on transmit as well. Yeah, and you see it is a little bit jumping back and forth, but you see that our NF frequency is spot on, and that is what we want. So yeah, you definitely can say that now our radio is totally spot on. Alright, now we have to adjust the bias current through our final here. So we have Q71 and Q72, which are our finals, and both should have around 100 and 120 milliamps idle current or bias current. So that means on SSB with no modulation we should read maximum the current through both, right? MOSFETs we should have 100 up to 120, maybe 150, but that might be already a little bit too much. And therefore first I've connected the amp meter to check what the setting is right now. And here you see our test probes connected, and here is our amp meter, and yeah, I leave it all as it is here, So you see here the contacts, and now I press here my PTT to see our bias current, and wow, 400 milliamps through the finals is, from my point of view, too high. So you know, there are many different radios with the same chassis on the market, and the Omega Force or the Ultra Force are dealing with the same final configuration with the ERF 2030. So they are dealing around 100-120 milliamps through the finals, and therefore I think we should realign it, otherwise it is no good idea. But let us start with our driver, and we have to set the bias current as well. So therefore let's here press our PTT, and let's see. So we have 33 milliamps through our driver, and I would say that is a bit too low. I would set it to, I would set it to 50. So let me see how I can arrange it here. So I need to go down to the pot, of course. Let me press PTT, and let's see if we can here increase it a little bit. And that is not given. Okay, so we have to leave it as 30. Alright, so we leave it at 30. Might be a little bit too low, but I think it is not harmful, but it is more important to get our finals right. Okay, so now it is connected for the finals, and both are now 366, and first of all I turn them both down, and that is already funny because they were not balanced. So now I take down the second one in a sec, and that is too much. So let me see what's going on here. I have to work around the camera, so I have to close it. Come on. Okay, so that is now good. So both are closed. So now when I press PTT, you see there is no current, and now I do the alignment for the first, which yeah, should be, so come on, should be on, let me say 60, around 60. Come on, that is already maybe a bit too much. Let's say, and you see how touchy that is. Okay, that looks fine. And now we take directly the second one. Let me go down here, and we try to bring it now together of 120 milliamps. So come on, 130, yeah, something like that. That looks pretty promising. I think I leave it. That is how I would arrange it. So that is fine. Well, and adjusting both finals individually helps that you do not need to buy paired parts, right? So you can buy whatever you want. You have two, in this case, ERF 2030, right? And or we can buy this both pots, adjust both individually to the right current. So that is to match them by setting, you know, the current individually. So that is the advantage we have it with doing it like this way. The next step I've done, I have aligned here our S meter. So we are sending into the radio with -73 dBm, which is an S9 level, and our meter is set exactly to S9. Okay, and the following steps I've done is aligning the receiver according our service manual, and as well transmit receive has been aligned by all the little transformers we have here, and then power level settings have been done for AM, FM, SSB. So you know, radio is now in factory condition, I would call it, and is working just fine. So really good sensitivity on SSB, FM and AM. So that is working just fine. A little tricky was to adjust here the 10, 20, 40 megahertz oscillator for our IF stage to convert down to 455 kilohertz second IF. So that was tricky, as we had the same problems as I have shown it to you with the carrier oscillator. So you really need a sensitive tester, or in that case counter. And yeah, so radio is back working, and I think I have really shown you all the critical steps, and you have seen what the impact is on SSB if you're too far away from the carrier. And therefore we are at the end of our video, and thanks for watching, and catch you next time.